Hi guys, so in this video what we're going to look at is the formula for the sum of a series, and we're going to prove it using induction. Okay, so this slide is just essentially telling you what's going on in a truly mathematical sense. We don't really have to worry too much about this, it's just telling you all the steps that we're going to go through here. But what I'll do is I'll show you on an example which will make this a lot more easier for you to understand. So we'll look at an example here, and you can see here I've already set it up, the bones of this. Now you need to set this up exactly the same way that I'm doing it. It's marks are given for the way it's set up as well as doing the maths. Okay, so what we need here is, this is the question, so we're going to prove by induction that this is true. We then have to go through step 1, step 2, this step here, and at the end then we have to do the definition just to show, or the conclusion I should say, showing that this is true. Okay, so the first thing we do is as follows. Read the question. It says prove by induction that 1 times 2 plus 2 times 3 plus, and you can see that what the pattern's happening here, it's one number multiplied by a number which is 1 greater is equal to a third n plus 1 by n plus 2. Now the first thing we do is we rewrite what we've got in the question there, and we just write p of n. Okay, and we just put a colon and we just rewrite exactly what we've just got. So we've got 1 by 2 plus 2 by 3 plus boom 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 n by n plus 1 is equal to a third n plus 1 by n plus 2. So we're just defining the problem, and we're saying that this is the PN. Now we're going to prove that this is true. So what we're going to do is we're going to find a starting number to stick this in, and the starting number here is, I hope you can see that the lowest number that we can stick in here is 1. So we're going to stick 1 in here. So I'm going to say, okay, well let's try p of 1 and throw it through. So if we do p of 1, what we're going to get here is we're going to get 1. So p of 1, we're just going to throw it in here, look. We're going to get 1 by 1 plus 1, which is 2, is equal to a third, on the right hand side now, of 1, 2, and n plus 2, which is 3. Okay, so let me run through that again. So what we're doing is we're going to put 1 through, and you can see here we're going to get 1 by 2 on the left hand side, okay, which is just this first term here essentially, that's why we picked 1, is equal to, and I'm going to put 1 through on the right hand side here to get a third by 1, 1 plus 1 is 2, 1 plus 2 is 3, just check to make sure that that works. Okay, should put a colon there. We get 2 on the left hand side is equal to a third of 1 times 2 times 3, well 1 times 2 times 3 is 6, 6 divided by 3 is equal to 2, and it works. The next thing we do is we change the variable, and we're going to assume that pk is true. And all we do for this is just write everything in terms of k. So p of k, okay, is 1 by 2 plus 2 by 3 plus, and you get k plus 1 is equal to a third k plus 1 by k plus 2. So all we've done is we've rewritten p of n in terms of k. Now what we're going to do is, now this is the linkage bit, we're going to prove k plus 1 and say it works. So remember, this is a whole domino effect, and what we're trying to do is we're trying to link each one, so we can get the link from one domino to the next domino. Once we push the first domino down, that's going to hit the next one, which is going to hit the next one, which hits the next one, which means that we can prove this to infinity, basically. Okay, so the next thing we do is we write, okay, pk plus 1. pk plus 1 is going to be essentially this same thing here on the left hand side, but what's going to happen is we're going to add another term on here. Then what we're going to do is going to replace all the k's here with k plus 1s on the right hand side as well, because we're just putting k plus 1 through the function. So what's going to happen here now is we're still going to get 1, 2, plus 2, 3, plus, and that's going to keep going. We're still going to get that k plus 1. But what we're going to do now is going to add another term on the end here. So that now is going to become equal to plus, I'll just do this in red so you can see it, k plus 1, and it's going to be k plus 1 plus 1, which is k plus 2. And that's now going to equal, on the right hand side, we've got to change all those k's for k plus 1 because we're putting k plus 1 through the function. So what's going to happen here now is we're going to get a third, and this first k is going to change to k plus 1. The second one here is going to be k plus 2, and this third one is going to be k plus 3. So what we're doing there is we're replacing each k with k plus 1. So this k plus 1 becomes k plus 2. This k plus 1 plus 2 becomes k plus 3, and this just k, this becomes k plus 1. And that there is the setup now to prove pk plus 1. Now if we can prove that this left hand side is equal to this right hand side, what we're saying is there's linkage so that all of those dominoes are now connected. And when I push down the first one, it'll hit the second one, which will make the third one, and that'll keep going forever and ever. Now here's the cool bit about induction, is what you, well, this particular way of induction, is that hopefully you can see that this bit here, this blue bit, I'm going to put an underline there, it's exactly the same as this bit here. Which means that we know that this left hand side up here is equal to this right hand side over here. And we're assuming that that's true. You know, that's the assumption. Which means that I can change all of this blue bit here for this expression on the right hand side. Which means that all of this here on the left I can change for this black bit here. So this now is going to come in for this. So my next line is a third k plus 1 by k plus 2 plus the red thing here. So this is going to come down. It's got the plus the k plus 1 by k plus 2 here, and that must equal the right hand side, which is a third of k plus 1, k plus 2 and k plus 3. Okay, so all we're going to do now is we're going to work on the left hand side and try and get it to equal the right hand side. So we're going to work exclusively on this side to try and make it equal to the right hand side. If we can prove the left hand side is equal to the right hand side, then we prove the linkage between the kth and the k plus 1 domino, basically. Okay, so let's have a look at the left hand side. You can see here we're trying to get a third on the right hand side, and we have a third here. We don't have a third here, so what I'm going to do is I'm going to try and get these so they have a common denominator. So I'm going to multiply that right hand term there by 3 over 3, so we can have a common denominator of 3 running through this. That now means I can start looking to take out common factors, and hopefully you can see here that we have a third, and we take out a third here. That's the reason why I've done that. So I've got a third, I'll take that out. We then can take out, hopefully you can see we have k plus 1 here and k plus 1. We can also take out k plus 2 because we've got k plus 2 and k plus 2 here. So I'm going to take out those factors. So I've got k plus 1, k plus 2. So those factors are already out. Okay, so let's have a look at each term now. So I already have the third from this term. I have the k plus 1 for that, the k plus 2 for that, which is great. Which means on this one, I'm left with just k in this term. So I'm going to open up another bracket. I'll put this in blue. That's just k. I'm going to do exactly the same and look at the other ones now. You can see here that they've already got the 3 that's on the bottom. I've got the k plus 1 there, k plus 1. I've got the k plus 2 there, the k plus 2. So anything I'm left with now is the 3. Okay, so it's k plus 3. And then look at that, that's perfect. That's actually equal to the right hand side. So you can see here that now that I've factorised it, I've got the third, k plus 1, k plus 2, k plus 3, which is now equal to exactly the same thing on the right hand side, which now proves the linkage. Once we've done that, we then have to go through, as I said, it's all about the way this is set up. So what we're saying now, thus pk plus 1 is true, assuming that pk is true, and thus pn is true for all values of n, where n is a natural number, and we're finished. I'll do another example on the next page, guys, just so we can run through it again, and hopefully if you didn't 100% get it this time, you'll get it the next time as we go through the second one. Okay, so again it says prove by induction that we have 1 plus 3 plus 9 plus, you can say this is another sequence. Okay, so the first thing we do is we have to prove that Pn is true. So we're going to write Pn first. So Pn, I'll put it here, P of n, and we're saying that 1 plus 3 plus 9 plus 3 to the power of n is equal to a half 3n plus 1 minus 1. So we're going to have a look to see what number we can stick through this to see what's going to work to start with. Well, again, you've got to come up with a number for this. If you put 3 to the power of 1 in here, so if we choose our n to be equal to 1, what's going to happen is we're going to get an answer of 3. And that isn't our first term, so we have to pick our n here in order to get the first term of 1. And we know that any number to the power of 0 is equal to 1, so our n here, we're going to check, is 0. So we're going to try P0 here instead of P1 like we did last time. So we just have to check that when we put our number in, will it get us to the first sequence or the first term in our sequence. So we're going to put P0 through this. I'll do it in blue. So we've got P of 0 through this. So we're going to put 3 to the power of 0. Okay, that's the 3 to the power of n here, 3 to the power of 0. And that should be equal to, on the other side, a half by 3 to the power of 0 plus 1, which is 1 minus 1. Let's work that out. And if we do that, we get 3 to the power of 0, which is 1, is equal to a half of 3 to the power of 1 minus 1, so that's a half of 2, which is equal to 1, and therefore we get the correct answer there. Okay, so the next thing, as we did before, is we just change all of the n's now. So we're going to assume that k is true, so p of k is equal to 1 plus 3 plus 9 plus 3 to the k. Okay, so anything that was an n before is just changed to a k, and that's a half of 3 to the k plus 1 minus 1. Okay, not an issue. So that's all just running through the systems. And now we're going to prove pk plus 1. So wherever we see a k, we're going to add a k plus 1. Remember, for this particular one, it's just adding another term to this. So what we're going to end up with on this one now is k plus 1 is going to be 1 plus 3 plus 9 plus 3 to the k. And then our extra term here, I'm going to do it in red, is plus 3 and k plus 1. And that's equal to, on the right hand side, all we're going to do is we're going to change all those k's. For k plus 1, there's only actually one of them. Okay, so this is now going to be equal to a half, and it's going to be 3 to the k plus 1 plus 1. Got the bracket there, minus 1. And what I'll do is I'll simplify that in a second. Well, I'll do it now actually. That's going to be equal to a half, and it's going to be 3 to the k plus 1, which is 3 to the power of k plus 2 minus 1. That's the right hand side done. Now, if you remember in the previous example, what we did is we said, okay, this 1 plus 3 plus 9 plus 3 to the k, which is this, can be rewritten as this right hand side here. So let's do that next. And if we do that, we're going to get a half, okay, 3 to the k plus 1 minus 1. So that there is this whole thing. That's all done. And then we've got the plus the 3 to the k plus 1 for the red bit, which is our extra term that we're adding in. Again, all we're going to do is going to deal with the left hand side and try and get it in terms of the right hand side, and hopefully we'll manage to get this all sorted. If we can, then we've proved it by induction. If we can't, then we haven't. So the first thing we're going to do then is we are going to do what we did last time, which is try and get this over 2, because we need to get the half in here. We have no half here at the moment, so just like the previous example, what I'm going to do is I'm going to multiply this by 2 over 2. Okay, and then what we're going to try and do is we're going to try and find some common factors again, if we can. That now means that I can take out the half as a common factor, which I'm going to do. Okay, so a half, and that means that if we have a look at what we can rewrite the first term here, so I've just taken the half out, so all that's going to remain where it is for now. I'll try and deal with that later. So that's going to be 3 to the k plus 1 minus 1, and on the other side what I have is plus 2 multiplied by, so 2 lots of 3 to the k plus 1 on the right hand side there. So if you're not sure what happened there, so what we have, the half has come out, half by 3k plus 1 minus 1 will give me this bit here. Okay, so that will give me that bit there. And then the second bit is we're adding, to get to this one, half times 2 will give me 2 over 2. So 2 over 2 there, and it's 3 to the k plus 1. Now hopefully you can see that we can combine this and this. We've got 2 lots of 3k plus 1 plus 1 lot of 3k plus 1, which means that what we're going to end up with now is a half by 3 lots of 3k plus 1 minus 1 is our next line. And now what we have here is we can actually write, if we write the index here, this is actually 3 to the power of 1. And you should remember from your index laws that 3 to the power, or sorry, I rephrase that, x to the power of a multiplied by x to the power of b is equal to x to the power of a plus b, i.e. all we do is we add the indexes, or the indices, and what we do there, that's what we're going to do. We're going to combine those two indices because we have the same base, and this is going to be equal to 3 to the 3k plus 1, so you can see it's going to be 1 plus k plus 1, which is k plus 2. So if we do that, we end up with a half of 3 to the k plus 2 minus 1, which is equal to the right hand side. So therefore we've proved the linkage. Again, then what we have to do is just finish it off. Thus pk plus 1 is true, assuming pk is true. Thus pn is true for all values of n, where n is a natural number. Now again guys, the maths isn't too tricky here. It's just spotting a few things, and it's all a bit of factorising. But what's really important is it is set out the way I've set it out in these slides. If it's not, you're going to lose marks in your exam. Okay?